Okay, let's start. Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulillah. So, inshallah, today we will solve recitation problem for chapter 11. We are done with chapter 11, but I will just remind you quickly what I said yesterday about conservation of angular momentum. So first, let me just remind you about these different quantities. So the first one is a torque. When I have rotation, the torque will play the role of the force. And the torque, as I said yesterday, is a vector quantity, R cross F. And that's the torque. Now, what will play the role of the linear momentum P if I have a rotation? P linear momentum is mv. What will play the role of linear momentum is what we call the angular momentum, L. And L is R cross P, P being mv. And this is a linear momentum for a single particle, okay? A particle-like object. Now, what is the angular momentum for a rigid body? The angular momentum for a rigid body is I omega. Okay. Angular momentum for a rigid body is I omega. And I can derive it, I can calculate it using the angular momentum of a single particle, because a rigid body or a solid has many single particles. So angular momentum for a rigid body is just the sum of the angular momentum of each particle. And again, for each particle, what is the angular momentum? The magnitude of the angular momentum is R P sine phi, or R perpendicular P, or R multiplied by P perpendicular. I told you that you can calculate it differently, right? So the angular momentum for each particle, I will use R perpendicular P. So it will be just R perpendicular P is mv. But you remember V is R perpendicular omega. So at the end of the day, I will end up with M R perpendicular square multiplied by omega. Now, when I sum it, I sum everything. Of course, this sum of mi r I square will give me the moment of inertia. Okay? And the omega will be the same because it's one rigid body. So basically, I will end up with L is sum of mi r I square multiplied by omega, which is L is I omega. And that's the angular momentum of a rigid body. Okay. I skip it, but you know, the demonstration is here actually, the derivation. Now, Newton's second law, when I have an object which is rotating, is net torque is I alpha, but alpha is derivative of omega with respect to time. So this I can get inside, I will have derivative as function of time of I omega, but I omega is L. So Newton's second law is just net torque is equal to the derivative of the angular momentum with respect to time. Okay. Net torque is derivative of L with respect to time. Now, when I have an isolated system is a system in which net torque is equal to 0. If net torque is equal to 0, that means angular momentum is constant. And I have conservation law. I have conservation of angular momentum. In an isolated system, in a closed and isolated system, meaning net torque is equal to 0, the angular momentum cannot change, no matter what changes happen in my system. But the total angular momentum of the system will not change. Okay? It's a constant of motion. Let me spell it out more clearly. If net external torque acting on a system is 0, meaning if I have an isolated system, the angular momentum L of the system remain constant, no matter what changes take place within the system. In a closed and isolated system, angular momentum is constant. Because net torque is equal to 0. Angular momentum initial is equal to angular momentum final. Now, this has a very, very practical, let's say, consequence. And sport people, ice skaters in Olympics, they use this beautifully. Divers, they use this beautifully. Whenever they want to rotate fast, they focus their whole mass in the center, in the axis of rotation. Okay? They shrink their body and they will rotate faster. So the example is this. You are sitting on a chair and the chair can rotate around the central axis. Let's say that the omega initial is 0. That means the angular momentum initial is 0. I omega initial is 0. When you are comfortably sitting, your angular momentum is 0. So no matter how fast you are moving your legs and hands, you cannot really rotate. In order for you to rotate, somebody has to rotate you, or you at least push your leg or your hand from the table and you exert a torque and you can rotate. But since your angular momentum at the beginning was 0, you can play with your hands, send your legs wherever you want. You will rotate with difficulty, because your angular momentum will want to remain the same. Now, once you are pushed and you have an initial angular speed of omega, now, no matter what you will do with your legs and hands, your angular momentum will remain the same. For instance, you are sitting and you are holding 2 dumbbells, okay? And you are rotating with an omega initial, angular speed omega initial. Now, what happens is when you bring the dumbbell next to your chest, you are decreasing the moment of inertia. Okay? And therefore, you are increasing the angular speed. You will go faster. Because this system which is rotating is left to itself. So net torque is equal to 0. So basically, I have angular momentum initial is equal to angular momentum final, conservation of angular momentum. Now, in the first case here, I'm extending my arms, meaning I'm taking a mass, the dumbbell, and I'm putting them far from the axis of rotation. So I'm increasing the moment of inertia. By doing that, I have to decrease the angular speed. Naturally, I will rotate slower. Okay. On the other hand, if I bring the dumbbell close to my chest, I am decreasing the moment of inertia, and the system will increase its angular speed, and I will speed up. Okay. And this is what ice skaters are using in Olympics. When they are rotating around themselves, when they want to rotate faster, they bring the body, close to the central axis. When they want to rotate slower, they extend their arms and legs and they go slowly, just by conservation of angular momentum. And the divers are doing that as well when they want to rotate faster, because they have these beautiful figures when they dive, right? So how fast you rotate, and this Olympics, I don't know if you know what I'm talking about. Anyway, and I sent you nice videos about the cat, for instance, and the cat is beautifully using conservation of angular momentum by rotating his upper body, or its upper body in one direction and its lower body in another direction. And he will always end up falling on his feet. Okay? Don't do that at home, because that's, that's dangerous. But when you take a cat, you put it upside down and you release it from, let's say, 1 meter, or it will fall down on its feet, because it will be using conservation of angular momentum, and he will be rotating by itself. So I sent you a couple of videos about that. Please have a look at them. I don't have time to discuss them extensively in class, unfortunately, but they are very interesting. And I sent you also a video about this NASA engineer who is building a squirrel-proof bird feeder. Okay, it's very nice. Okay, what's the process, the thought process behind what are the challenges he's facing and how he's tackling them? Okay, those who watch it, you know what I'm talking about. Okay, so now let me go to the recitation problems. So I already talked about this last time. You know how to calculate the moment of inertia of any of these objects, okay? And you know parallel axis theorem. And I already reminded you about this as well. So let's go to this problem first. Here we have, in this figure 8, we have the angular momentum magnitude, L, as a function of time. So rank the 4-lettered time interval according to the magnitude of the torque acting on the wheel. So I give you L versus T. You know that torque is derivative of angular momentum with respect to time. So here I have an angular momentum L versus T. So this torque is a slope, it's a derivative. Okay, of course, I'm talking about absolute value here. So absolute value everywhere. So D has the largest torque, okay, because it has a, you know, steepest slope. The slope is large here. Then B is the second largest torque in magnitude. I'm talking in magnitude, okay. And then you have, of course, torque of B and torque of C and torque of A are equal to 0 because the slope is equal to 0. Okay, these slopes are equal to 0, so these are the smallest. Now, I can ask you the other way around. I will give you a torque as a function of time. And I will ask you, what is the angular momentum? You know that torque is derivative of angular momentum with respect to time. That means dl is torque dt. That means if I integrate, if I take the integral, I will have delta L, which is L final minus L initial, is equal to an area under the curve. Area under the curve, but which curve? A torque versus time curve. Okay. So that means my L final is the angular momentum at t equal 3 seconds, is the angular momentum at t equals 0 second, plus the area under the curve, and the area is between 0 and 3. So you have the area of this triangle, the area of this rectangle, and of course here the area is 0. So technically I can stop the integration at 2. Okay. So that means my L final, my L at 3 is L initial. By the way, I gave you omega, I gave you moment of inertia, and I gave you omega initial, omega naught. So you can just multiply them and you will get it, plus the area under the curve. Okay. And that will give you a final angular momentum, L at t equal 3, which is equal to 4 kilogram meter square divided by second. Okay, be careful with the units. Angular momentum, what are the units of angular momentum? Of course, is I omega. Okay, so you know the units of I, it's kilogram meter square. Omega is radian per second, so you divide by second. This is a unit for angular momentum. But also you know that it's torque multiplied by time. So torque is Newton meter multiplied by time, which is second, okay, which is the same. So these are very simple questions. Now, in the exam, the simple questions and the difficult questions have equal dignity. All of them, they will cost you 1 point if you miss them. So don't be like my best students. They miss the simple questions. I have a good student last semester. He missed the simple question and he got all the difficult questions. At the end, he finished with A+, of course. But, you know. On the other hand, I have another student, difficult or easy, he scored 100% in Physics 101, mashallah. And that's what I want you to do, okay? So these are simple questions. Now let's go to something more elaborate. Now we will study rolling. So here we have a uniform solid sphere. What is the moment of inertia of the uniform solid sphere? Who can tell me? Uniform solid sphere. Muhammad Farhan.
MR square. I don't remember.
You check the formula sheet, mr square, it will be 2/5.
Okay.
Once you solve the recitation problem of chapter 10, this, you have to check, of course, in the formula sheet, okay? But this will come quickly, 2/5 of mr square. If it's a hollow sphere, it will be 2/3 of mr square. So it's 2/5 of mr square, and I give you the mass of the sphere, and I give you the radius r. It rolls smoothly from rest down a ramp. And I give you the angle of the ramp, 30 degrees. The question is, what is the magnitude of the frictional force on the ball as it's rolled down the ramp? Of course, this frictional force is a static frictional force. And I already said that in class. But let me remind what I said in class. This problem was solved in class, by the way, already in the Al-Jalal slides. And we gave it in the exam. You have people who missed it again. The same problem has been solved in Al-Jalal slides. And I solved it in class. So here I said roll smoothly. It's a smooth rolling, or rolling without slipping, or rolling without sliding. You know that when I have a smooth rolling, the velocity of center of mass is r omega. Let's take in magnitude. The magnitude or the speed of the center of mass is r multiplied by the angular speed. And the acceleration of the center of mass is r alpha. The linear acceleration of the center of mass is r, the radius of my solid, which is rolling, multiplied by the angular acceleration. And as you know, rolling is a combination of translational motion. So I translate my center of mass has a translational motion, but also I have a rotation around the center of mass. Okay. Good. That being said, let me draw. This is my ramp. Here I gave you the angle theta is 30 degrees. My object starts from rest on top of the ramp. So this is my object. It's a uniform solid sphere. Okay, let me use this here. Okay. So it starts from rest. What is my initial speed? The velocity of center of mass is 0 because I start from rest. And what is the initial omega? Is 0 as well, because omega is V initial divided by R. Okay. So I start from rest. Of course, I was not rotating, but also I was not translating down the inclined plane. Now, once I release it now from rest, the ball will roll smoothly downward. Now my ball is somewhere here now. Okay. So the ball is rotating around the center of mass, but also the center of mass itself has a translational motion down the inclined plane. So this is the acceleration of center of mass downward, right? Okay. Now, of course, what should be the direction of rotation? The ball, should it rotate clockwise or counterclockwise here? Just by physics.
Counterclockwise.
Counterclockwise. Thank you, Mohammed. It's plus. Okay. Why it's rotating counterclockwise? Because I have a force of rolling. Okay. I have a force which is creating the rotation of my ball. And that force is a frictional force. And it's a static frictional force. It's Fs. And I want the magnitude of this static frictional force. Okay. So you see this static frictional force has a torque which is positive. That's why the ball is rolling counterclockwise. Because actually my ball has a weight. This is the gravitational force of the ball. And this is a normal force of the ball. Normal force due to the incline. But these two forces have zero torque. Why? They are not able to rotate my ball because they have a moment arm which is 0. They are radial forces. They are passing through the axis of rotation. So they are not causing a rotation whatsoever. So the only force which is doing a rotation here, which has a torque, is a frictional force. And it's a static frictional force. Why it's a static frictional force? Because as I told you in class, momentarily, when I look at this point of contact, it's always at rest. The ball is not sliding down. Okay, so I have a smooth rolling. In a smooth rolling, I have a static frictional force, Fs. Okay, and the static frictional force has something very special. The work of the static frictional force is 0. It does not work, but at the same time, the torque of the static frictional force is different from 0. So the static frictional force is not dissipating energy to the environment. It's only here to make my object roll smoothly down the inclined plane. It has a torque. And by the way, what the torque of the frictional force? It will be just plus FSR. The moment arm here is the radius of my disk. I'm saying this because it's important. I can solve this problem in 2 seconds, but I'm just reminding you the context. So you know that it's a static frictional force. The work of a static frictional force is 0, and the torque of static frictional force is different from 0. Now, that being said, this is because it's a smooth rolling. A rolling without slipping or a rolling without sliding. But if it was sliding, I will never give you that case in a Physics 101 course. If it's sliding, of course, you know what is the work of frictional force, kinetic friction, minus FKD. Okay. But this is not true here because I have a smooth rolling. So if I did not have frictional force, my ball, no matter how his geometry looks like or its geometry looks like, it will not roll. It will just slide like a box. Okay. So if there was no friction, the ball will just slide like a box because there is no torque on it. Okay, good. Now, that being said, that's just a kind reminder of the lecture. Now let's go down to the problem. Of course, when you solve this in the exam, you don't need to go through all this. I'm just saying this because I'm explaining. If you go in an exam, you go straight to the point. So here I want the magnitude of frictional force. As I said, I have a translational motion and a rotational motion. So let me apply Newton's second law for the translational motion. Of course, here I will have, this is my x-axis along the inclined plane. I will apply Newton's second law along the x-axis. I will have plus Fs minus the x component of the gravitational force, basically this x component of the gravitational force, which is minus mg sine theta. And this is equal to minus m acceleration of the center of mass. Okay. So this is my first equation. Meaning, if I know the acceleration of the center of mass, I know the frictional force. Now, the acceleration of the center of mass in magnitude is already given in your formula. In magnitude, well, let's put it in direction. In direction, I said acceleration center of mass along x. In the formula sheet is just minus g sine theta divided by 1 plus moment of inertia divided by mr squared. But this minus is just to tell you that it's already downward. And you see here, I already put it here. So here I'm talking about the magnitude of the center of mass. So this is, let me take the magnitude, of course. If I take the magnitude here, it will be plus. So now I will take this acceleration of center of mass in magnitude. I will just plug in this equation and I will get what is Fs. I know m, I know g, I know sine theta, I know m, I know acceleration of center of mass from the formula sheet. Of course, be careful. Okay? Either I put the minus here, and here I'm talking about in magnitude. Either I put a plus here, and here I have a minus. So you should know what I'm talking about here. Okay. So here the minus is put outside. So here this is a magnitude. So here I have to put a plus. Now you plug it here, and you will get 8.4 Newton, and this is your static frictional force. Now, for those who wants to know or who did not come to class, who wants to know where this formula is coming from, this formula is coming from this equation 1, where I have two unknown, Fs and acceleration. Now I have to find the second equation. I will look at the rotation. The rotation, I will have net torque is I alpha. As I told you, only the torque of frictional force is different from 0. The frictional torque of the frictional force is Fsr, and this is equal to I alpha. But alpha, as I have a smooth rolling, alpha is just acceleration of center of mass divided by R. Okay, acceleration of center of mass divided by R. Okay, and then I have my second equation, two unknown, Fs and acceleration of center of mass. I play with these two gentlemen and I will get the acceleration of center of mass, and then I will get Fs as well. Okay, you have a system of two equations, two unknown. Okay, so yeah, so if you want to get the acceleration of center of mass, the formula, you have to combine the Newton's second law for the translational motion and Newton's second law for the rotational motion. Okay, good. Is it clear or not?
Yes, it is.
Now, let me go to the next problem, which looks the same. But here I have a uniform solid sphere. Oh, I is 2/5 of mr squared. M is the mass of the solid sphere and R is a ring. It rolls mostly without slipping. Well, I know that V center of mass is R omega. Let me talk everything in magnitude. And magnitude of the acceleration of center of mass is equal to what? R alpha. And what is the magnitude of the acceleration of center of mass? You can look at your formula sheet. Is minus g sine theta divided by 1 plus moment of inertia divided by mr squared. If I talk about magnitude here, it will be a plus. If I want to talk about direction, of course, here I have a minus because it's downward. Okay? So let me talk about magnitude. So I will put a plus here. The minus is just tell you it's downward, down the incline. Okay, so this object here is rolling smoothly with a center of mass velocity of 2.5 meters per second along the horizontal table. Then it's climbed up a ramp incline at 20 degrees. Now the question is, what is the maximum distance traveled by the center of mass of the sphere along the ramp? I will draw as usual. This is my horizontal, and this is my inclined plane. I know that theta here is equal to 20 degrees. My uniform solid sphere or my ball is rolling, so it has an angular speed, but also I know the velocity of the center of mass is 2.5 meters per second. Okay, and it's rolling. I know that it's rolling in this direction. Why? Because you know why. Now it's rolling up the inclined plane. Now at maximum height, of course, it will stop. At maximum height, let me call it h, it will stop. So my linear velocity will be 0, but also my angular velocity will be 0. Okay, he will stop not only translating along the inclined plane, but also he'll stop rotating. Okay, my uniform solid sphere will stop. So the final kinetic energy is 0. Okay. Now the question here is, what is the distance traveled by the center of mass? What is this distance here? That's the question. Find D, not H. I want D. So how should I do? Any idea? So as I told you, since it's rolling because there is a frictional force and it's a static frictional force. So the work of the static frictional force is 0.
Doctor, we find H, then we find D.
Exactly. That's correct.
Okay.
Okay. But how? That's a question. How?
By work kinetic energy here.
You can use work kinetic energy theorem if you want, but you can use better conservation of mechanical energy.
Yeah.
Yes, they are the same, by the way. Okay, but here, let me just tell you, as you know, it's rolling because there is a static frictional force, and work of static frictional force is 0 because it's a static frictional force. On the other hand, work of kinetic frictional force is not 0, it's FKD. But this is not true here. Why? Because I'm not slipping, I'm not sliding. I have a smooth rolling. So I have a static frictional force. So work of static frictional force is 0, but torque of static frictional force is different from 0 because the static frictional force will make my object roll. Otherwise, it will just slide and go up. Okay, so work of static frictional force is 0 means I have conservation of mechanical energy. I don't have dissipation. I don't have heat, okay, lost to the environment. So
I don't have change in thermal energy.
I don't have thermal energy at all.
Okay.
That's what I mean. Because work of thermal energy is coming from friction, right?
Yes.
There is friction, but it's a static friction. So that's why locally it's not sliding. The V at the contact point is 0. And I gave you a nice example last time, and I told you, if I take a box and the box is rolling down, I touch the surface of contact, it will heat. I will feel some heat because it's kinetic friction. And kinetic friction is doing some work, minus FKD, and that's thermal energy. If I take a cylinder, same mass, same material, okay, rolling down, when I touch it, it will not heat. When it comes down here and I take it and I touch it, it doesn't have any heat, no thermal energy.
Okay.
Because it's a static friction, okay? And static friction is not doing work. So that being said, that means I have conservation of total mechanical energy. I have conservation of mechanical energy. Delta K plus delta UG is equal to 0. There is no FKD, okay, because it's a static friction. So what is delta K? It will be K final, and K final, we already talked about it, is 0, minus K initial. Now, what is K initial? K initial, you have to take into account 2 things, because it's rolling. It has a translational kinetic energy and a rotational kinetic energy. The rotational kinetic energy is half I omega square, and the translational kinetic energy is half m v square. I call it capital M, so let me keep it capital M. Now, what is delta UG? Of course, if I take the ground as my reference, this is UG initial, I end up at here, so it will be UG final, which is MGH. So plus MGH. And this is equal to 0. By the way, H is equal to D sine theta, because I don't really want H, I want D. So I will have MGH, but H is D sine theta. I know everything here, only D is unknown. This is equal to half I. Now I will write it as 2/5 of mr square omega. Now omega, I will not write omega, I will just say V center of mass divided by R. Omega is V center of mass divided by R. So it will be 2.5 divided by R, because I already gave you the V center of mass. So it will be V square divided by R square. I replace omega by V divided by R, plus half mv square. Okay. Now I have mass everywhere, so the mass, that's why I did not give you the mass, it simplifies. Okay. What else will simplify? Here I have R square, and this R square will go away. So I will have GD sine 20 degree is equal half, and this 2 will go away. I'll have 1/5 of V square plus 1/2 of V square, which is 7 divided by 10 V square. And V being this 2.5. So my only unknown is D. So I know everything else. I get D, and D will give me 1.3 meters. Okay. And here I have been using conservation of mechanical energy. Okay. And I solved this problem in class, by the way. Okay. Now, there is something more to this. There is a shortcut. The shortcut is, I know the acceleration of center of mass if my object is rolling. The acceleration in magnitude is G sine theta divided by 1 plus moment of inertia divided by mr squared. Here, moment of inertia divided by mr squared is equal to 2 divided by 5. I divided by mr squared is equal to 2 divided by 5. So I know actually the acceleration of the center of mass. So I know the linear acceleration, but also I know the initial velocity. Initial velocity is 2.5 and final linear velocity is 0. So chapter 2, I will say V final square is equal to V initial square plus 2AD. V final is 0, V initial is 2.5. I know 2A. A is equal to what? G sine 20 divided by 1 plus 2 divided by 5. And here the only unknown is D. And you do it, you will get the same answer, 1.3 meters. But conceptually, the first way is better, because in the first way, you need to be aware of what is conservation of mechanical energy, okay? What is rotation, what is the energy for rolling, you know? So I will definitely prefer this, okay? Because it has more physics substance, physical concept. Here, all what you need to do is just know, a prep year student know how to solve this easily, okay? Because this is just asking chapter 2. But he's not aware of the, you know, the spices in rolling. Well, he's aware of it because he knows rolling. Anyway, so all the ways will give you the same answer, and that's what I'm looking for. Okay, now for this problem here, let me solve it very quickly. So we have a horizontal force F applied, which is equal in magnitude to 10 Newton. Okay. It's applied to this wheel, and the wheel has a mass m, which is 10 kilogram, and a radius which is 0.3 meters. So the wheel rolls mostly on a horizontal surface, and I give you the acceleration of center of mass is 0.6. So the acceleration of center of mass is 0.6 meters per second squared. So the question is, in unit vector notation, what is the frictional force of the wheel, on the wheel? So of course, I know that it will be a static frictional force, and I have to have a frictional force for the wheel to roll. Otherwise, if there is no friction, if it was ice here, the wheel will just slide, but without rolling. But because there is friction, what is the direction of the frictional force? The tendency to slide is toward the right. The frictional force will oppose the tendency to slide. So this is Fs. So Fs is along the negative x direction. And Fs will cause a clockwise rotation, okay, in the negative direction, because Fs will make my wheel rotate in the clockwise direction, in the negative direction. Okay, so it's a rolling. I have a translational motion. So let me apply Newton's second law to the translational motion along the x direction. Along the x direction, I will have F applied minus Fs is mass of my wheel multiplied by the acceleration of the center of mass. So 10 minus Fs is equal to the mass, which is 10, sorry, multiplied by the acceleration, which is 0.6. So Fs will be equal to 4 Newton in magnitude. Now in unit vector notation, of course, Fs vector will be minus 4 Newton I hat in the negative x direction. Now the second question is, what is the rotational inertia of the wheel about the center of mass? About a rotational axis passing through the center of mass. I want I. So how do I get I? I will say something very simple. Let me first get alpha. I know acceleration, it's a smooth rolling. So I know acceleration of center of mass is just R alpha. So that means alpha is the acceleration of center of mass divided by R. Basically it will be 0.6 divided by 0.3. So I know alpha. Alpha is 2 radian per second square in magnitude, of course, because in direction, I know that alpha is negative. Okay? Because alpha is clockwise, so it should be negative, but in magnitude, it's 2 radian per second. So now once I know alpha, I will just say, oh, net torque in magnitude is I alpha. Okay? So that means I is net torque divided by alpha. Now, what is the net torque here? Only the frictional force is doing a torque. Okay, so in magnitude, let me take it everything in magnitude. So net torque will be FSR. I know Fs, I know R, I know alpha, so I know what is moment of inertia or rotational inertia. Fs is 4, R is radius, I know it already, I know alpha, so I know what is the moment of inertia. Okay? But in reality, the torque of the friction is negative. Okay? But here I just get rid of it by taking an absolute value. But in reality, the torque of Fs is negative, the alpha is negative. Negative divided by negative will give you a positive moment of inertia. So the moment of inertia is just 0.6 kilogram meter square. Now let's go to something more important and more interesting, which is conservation of angular momentum. For the 10 minutes remaining, I want to solve this problem, then this problem, then this problem, then this problem. So let's see how far we will go. Let's start by this problem here. So we have a bullet, and I give you the mass of the bullet. I will call it MB. MB is 50 10 to the power minus 3 kilogram. Okay. 50 gram, I put it in kilogram. So it's fired horizontally at one end of a 0.6 meter long uniform rod. So the rod is uniform, and L of the rod is 0.6 meters. And I give you the mass of the rod. Mass of the rod, I will call it capital M, half kilogram. And the rod is initially at rest. So omega initial of the rod is equal to 0. So this rod can pivot about this end. Okay, this pivot point. The pivot point is at the edge, at the end of the rod, A. Okay, so the axis of rotation is pointing towards you. Okay. Good. Now, as shown in the figure below. Now, the question is, if the angular speed of the system, bullet plus rod, assumed to stick together after A, about A, just after impact is 4.5 radian per second, what is a bullet speed just before impact? So here what I did here, I came here and I just fired the bullet here with the VB. And I fired it horizontally. And the bullet will stick to my rod, okay? Because that's what I said here. So now this is initial. Final is looks like this. So the rod is here. And now the bullet is fixed here. So it sticks to the rod, and the whole thing will have an omega final, which is 4.5. Yes, somebody has a question?
It will be like completely an elastic collision.
Good point. Exactly. It will be like a completely inelastic collision. But I will not talk about this here, because here I'm rotating. Okay. So I will just say conservation of angular momentum. Because a collision, whether it's elastic, inelastic, completely inelastic, I have conservation of linear momentum, always. But here, since these objects, the rod can rotate, I will talk about conservation of angular momentum. Okay. It's like a completely inelastic collision, you're right, but which is just a collision. Completely inelastic collision is a collision, and every collision have conservation of linear momentum. But here it's rotating, it will be conservation of angular momentum. That's a good point. So my system is made of the bullet plus the rod. Okay, this is a whole system. Now the bullet and the rod has net torque equal to 0. Okay? Because there is a collision, there is an impact, but the impact force are internal force. When I talk about net torque, I'm talking about external force. So net torque is equal to 0. That means I have conservation of angular momentum. L initial is equal to N final, but L initial of the system will be equal to L final of the system. Now, what is L? Is the initial angular momentum of the whole system. L initial of the system, of course, will be L initial of my rod plus L initial of my bullet. Do you agree with me? Now, what is the angular momentum of the rod? Is I multiplied by omega initial of the rod. This is equal to 0 because I said it at the beginning, the rod is at rest. So the rod at rest has an angular momentum 0 because it's at rest at the beginning and omega 0 rod is equal to 0. Now, what is the angular momentum for the bullet? The bullet is a particle-like object. So you know that L is R cross P. So the magnitude of L is RP sine phi. So it will be R mv sine phi. Now here, look at my bullet here. The bullet is fired horizontally and my rod is vertical. So R is this distance here. Okay, this is R. P is like this. P is mv. And phi is the angle between them. So here, what is equal to the magnitude of R? The magnitude of R will be L, the length of my rod. The mass of the bullet is mb. The V of the bullet will be VB. And the sine phi will be sine 90 degree, which is 1. So my initial angular momentum is just L, mass of the bullet, speed of the bullet. Do you agree with me? Okay. Now, what is the final angular momentum of my system? The final angular momentum of my system is just I final multiplied by omega final. Okay. By the way, I know omega final. Omega final is 4.5. But what is I final? I final is simple. I have a rod. So I final will be I of the rod, but the rod, the axis is not passing through the middle, it's passing through the edge, parallel axis theorem. So it will be 1/3 of ml square. But also I have to add the moment of inertia of this particle-like object, which is fixed at the end. So I'll have mass of the bullet multiplied by L square because it's at a distance L from my axis of rotation, which is here at A. So this is the omega final. So bottom line, I will have this. This is equal to 1/3 of mass of the rod L square plus mass of the bullet L square multiplied by omega final. And my only unknown here is this VB. Okay, so I just divide by L divided by MB. And I will get a VB of 12 meters per second. You get my point? Is it clear? No. If it's not clear, tell me now, because this will come in the exam. Muhammad Farhan, you are the only one talking to me now. So, don't leave me hanging. What do you think? Okay.
That's okay.
Okay. Now, let me make it a little bit more complex. The others did not have lunch, so I guess that's why they are not replying to my questions. But you will reply to my quizzes, inshallah. Okay, so that's the thing. And by the way, in this solution that is given, there is a typo. So you have to find the typo. Okay? The solution that I posted, you know, there is a typo here. Okay? Now, let's solve this problem, which is even more important. It's the same type of problem. Okay? So I have my uniform rod. Now the axis is not passing through the edge. The axis is passing through the center. Well, I know moment of inertia of a rod when the axis is passing through the center. What is it? 1/12 mass of the rod, length of the rod squared. Formula sheet. Now I give you the mass of the rod, the length of the rod and the mass of the rod. This is L and this is the mass of the rod. And it can rotate. Now here what I did is I will fire the bullet, but a certain angle here. Now the angle is not 90 degree anymore. Now the angle is 60 degree. Okay. So you will apply the same thing. Now the question here is, now of course, I said it somewhere here. If the bullet lodges in the rod and the angular velocity of the rod immediately after collision is 10. So this is my initial here. My final will be, I have my rod and the axis of rotation is here. Now the bullet was launched. Now the bullet will lodge here and stick here. And the whole system will have an omega final of 10 radian per second. So the question is, what is the bullet speed? What is VB? VB being here. What is VB? In the 1 minute remaining, let me solve it. I will also have conservation of angular momentum. My system here is bullet plus rod. Okay, so angular momentum of the system before initial is equal to angular momentum of the bullet, of the system, sorry, final. Initially, the rod was at rest, so omega initial of the rod is 0. So angular momentum of the system initial is the angular momentum of the rod plus angular momentum of the bullet. For the rod, it's simple. It's I, and I is 1/12 of ml squared multiplied by omega. But omega is 0, so this part is 0. Now, what is the angular momentum for my bullet? The bullet, the angular momentum is RMV sine phi. But here the sine phi is equal to 60 degrees. And R is the distance between the axis of rotation and the bullet just before rotation, just before collision. So what is R here? Who can tell me what is R? L by
Pythagorean theorem?
No, it's just the half of the length, actually. Because just before collision, you look at it here.
Yes.
Okay, so it's just half of the length. Mass of the bullet multiplied by speed of the bullet sine 60 degrees. So here I will have half of the length, mass of the bullet, speed of the bullet multiplied by sine 60. And this is equal to L system final. So what is L system final? It's I final, omega final. By the way, omega final is 10 radian per second. Now what is I final? I final is I of my rod plus I of my bullet. So it will be 1/12 of ml square plus, now here I have a particle of mass m, b, at a distance L divided by 2 from my origin. So it will be L divided by 2 square. That's it. So here I will have 1/12 of ml square plus mb L square divided by 4 multiplied by omega final. And this is equal to this. The only unknown is VB. The rest, I know everything. I know L divided by 2, I know MB, I know sine 60, I know everything. The only unknown is VB, so I just divide and I get the right answer. Okay, so let's stop here. It's time. And I lost a couple of students already, mashallah. So let's stop here. I wanted to finish this, but I will record the rest of the problems, okay? I will record them and you can watch them whenever you can. So thank you very much and Assalamu alaikum.
Thank you, Doctor.
Is it clear, Muhammad Farhan?
Yes.
Thank you all and see you tomorrow, inshallah. Assalamu alaikum.
Doctor.
Yes.
The quiz is on Tuesday or Thursday?
It will be on Thursday because some students said the majority want it on Thursday. I'm still waiting for the result of the survey. So that will give you VB, okay? The speed of the bullet just before impact. So that's exactly what I did here. Okay, in the solution that I gave you, this is what I did here. Okay, the moment of inertia is 1/12 of ml square. And I give you the mass of the rod, the length of the rod, because the axis of rotation is passing through the middle here. So conservation of angular momentum will lead to this. This is the initial angular momentum of the bullet. Initial. The angular momentum of the rod initial is 0 because you have I omega 0, but omega 0 is 0, this is 0. And this is the final I final. This is I final, and this is omega final. So angular momentum initial is equal to angular momentum final. And again, here's this R here is L divided by 2. Okay. And also this R here is L divided by 2. So that's what I did here. Okay. So V is the only unknown. So it will be 1/12 of m L square plus m R square, but R is L divided by 2, as I said. Okay. Divided by R, which is L divided by 2. Why? Because this R here is L divided by 2. This is R, and in magnitude is just the length of the divided by 2. Okay. Multiply by m, multiply by sine 60, and you get the speed of the bullet before collision. Now let's go to this problem here, which is an A+ problem. So read it carefully. I have a rod, and this rod, the pivot point is at the edge here. So first, you know what is the moment of inertia, 1/3 of mL square. If m is the mass of the rod, and I give you the mass of the rod here, 3m0, m0 being half kilogram, and I give you the length of the rod, which is half L. Sorry, L and a half, so 1.5 L. Okay. And this rod can rotate in the vertical, about the vertical axis through this end here, which is at the edge. So initially it's held horizontally. When it's released, so that means my omega initial here is 0. Okay, meaning my kinetic energy of rotation here, initial, is just 0. So now when it's released, this rod can rotate, and it rotates down. Now the question is, what is the omega I here, just before when it hits this block of mass m0? So once I get this omega initial, omega I, which is different from this omega naught, okay? Now it hits this block and they stick together. I said it here, okay? When released, it swings through the lowest position. So I have to find what is the omega at the lowest position and collides with a stationary block of mass m0 that stick to the end of the rod. So they stick together. Now the question is, what is the angular speed in radian per second of the rod block system immediately after collision? What is this omega final here immediately after collision? So as Mohammed Farhan said, it's a completely inelastic collision. Okay, but it's a rotating object. So I will not have conservation of linear momentum. I will have conservation of angular momentum. Net torque is equal to 0. I have conservation of angular momentum initial is equal to angular momentum final. I have to first define what is my system. The system, of course, is rod plus block. And of course, ignore all forms of friction. So I will have conservation of mechanical energy. So the first thing first, I will have conservation of angular momentum at the end. So I'll have I initial, omega initial is equal to I final, omega final. Okay. Now the question is, what is this omega final? Okay. So omega final will be what? I initial divided by I final multiplied by omega initial. But first I have to find what is this omega initial. Let's go and find the omega initial. Now omega initial, I will use what? Conservation of mechanical energy. Delta K plus delta UG is equal to 0, chapter 8. But here also I will use chapter 9 plus chapter 10. Okay. Now K final. K final is half I omega final square. But this omega final, I call it omega initial, omega I square, minus half I omega 0 square. So this is 0 because omega 0 is 0. Plus delta UG. Now what is delta UG? I have solved many problems that looks like this. So I have to first locate the center of mass. And I look the change in height in the center of mass. It's a uniform rod. The center of mass is right here in the middle. So the change of height of the center of mass is just H is just L divided by 2. So it's going down, so it will be minus mg L divided by 2. And this is equal to what? 0. So I will have half I, but I is 1/3 of ml square multiplied by omega initial square. Omega initial is the omega when my rod is at the lowest point. So this will be equal to M, of course here is capital M because it's mass of the rod, G L divided by 2. You see the M will simplify, this L here will simplify with this L, this half here will simplify with this half, and I will get omega initial is square root of 3G divided by L. So this we have already solved this type of problems many times in chapter 10. So this will give me 4.4 radian per second. Now I know omega initial. So I will come here and I will plug it here. Okay. Now I need to know what is I initial and I final. Well, I initial is known. I initial is just 1/3 of ml square. It's in the moment of inertia of the rod. Now what is I final? I final will be I initial, basically the moment of inertia of the rod. But now I will have a mass m at a distance L from my pivot point. Okay. So I final is 1/3 of ml square plus m0 L square. So my omega final will be I initial 1/3 of ml square divided by 1/3 of ml square plus m0 L square. You see the L square will go away anyway. Multiply by omega initial, and omega initial is just 4.4. Okay, and this you will find an omega final of 2.2 radian per second. Okay, just by conservation of mechanical energy. And this is an A+ question because it's combined chapter 8, chapter 9, chapter 10, and chapter 11. Okay. Conservation of angular momentum is a powerful tool. Now let's solve this problem here. So here we have a disk, which is like a merry-go-round. So this is my disk, and the disk is rotating clockwise or counterclockwise. Okay. The disk has a mass m and a radius r, has a moment of inertia 2.5 10 to the power 2 kilogram meter square. So I know the moment of inertia. The axis of rotation is here. So omega initial of the disk is 1.7 radian per second. Okay. Now there is a child. Now the child is moving this way. Okay, radially. Okay. So the speed of the child, v, is radial. Okay. And then the child sits here. Now the question is, what is the new angular momentum? What is the new angular speed of the disk? So my system here will be child plus disk. Okay, and I will have conservation of angular momentum. Angular momentum of the system initial is equal to angular momentum of the system final. Now what is the angular momentum of the system initial? So angular momentum of the system initial is just the angular momentum of the child plus the angular momentum of the disk initial. So what is the angular momentum of the disk? This is easy. This is moment of inertia, 2.5 10 to the power 2 multiplied by omega naught, which is 1.7. Now this I have to add it to the angular momentum of the child. Now what is the angular momentum of the child? The child will be a particle-like system. So the L is just R cross P. So magnitude of L is RP, which is mv sine phi. Okay, but here the child is coming radially. So P, which is mv, is radial. So this is R here. So the angle between them is 180 degrees. So sine phi is equal to 0. So in reality, this children or the child angular momentum is 0. Not because he's not coming with a speed. It is coming with a speed, but he is radial, okay? This R cos this P here is equal to 0, okay? So this will be equal to the angular momentum final. Now, angular momentum final of the system is just the merry-go-round plus a child of 25 kilograms sitting at the edge. So it will be I final, omega final. So what I want is this omega final. So I final will be I of the disk plus mass of the child, and the child is at distance r from the axis of rotation, r squared. Okay. So basically omega final is I divided by, meaning I disk here, okay, because this is I disk here. It will be I disk, which is basically this number. This is I disk plus m, mass of the child, 25 kilogram, r square, and r being the radius 2 meters. And this, of course, multiplied by omega naught. So I know everything. I know I disk, I know the mass of the child, I know r square, I know omega naught square. So my final answer, I get it easily. Okay, by conservation of angular momentum. This is how powerful angular momentum is. Now, this is exactly what I did here. Okay, this is exactly what I did here. Conservation of angular momentum. So here, of course, you have to say that the angular momentum of the child is 0. This is the angular momentum of the disk initial. And this is I final, and this is omega final. Because now the child and the disk form one system. And I know what is the moment of inertia of the whole child plus disk. Since this child is sitting on the edge, and you get omega final. Good. Now I will give you a more complex problem. Same problem, but look what we will do now. This is how you will improve. Now, instead of the child going this direction, what if the child is jumping this way, tangentially? And I give you V of the child. V child, let's say 2 meters per second. And the child jump now tangentially and sit here. So how it will be. Okay. Now what about another child? So this child MC, let's say this child has a mass MC, 25 kilogram. What about another child here jumping in this direction here? Let's say Bilal, I will call it MB. Let's say 40 kilogram. And he's jumping with a speed of V Bilal, let's say 1.5 meters per second. Okay. And they jump at the same time. What will be the final omega final of the whole system? You get my point? And by the way, I can say that you have another child, let's say Muhammad Farhan, okay, and he's jumping now, not tangentially. Now he will jump with a certain angle. Let's say he will jump with a certain angle. Okay, with an angle which is, let's say, theta, which is 20 degrees. Okay, so this is Muhammad, MM, and the mass of Muhammad, let's say, is child named Muhammad, let's say 30 kilogram, and the V of Muhammad is, let's say, 3 meters per second. And all of them are sitting at the edge. Can you solve that problem? And all of them are jumping at the same time. So what is the new angular speed just after all of them jump and sit at the edges? You will be using conservation of angular momentum. Now your system will be the disk plus child C plus child B plus child M. So now you have to say angular momentum of the system initial should be equal to the angular momentum of the system final. Now, what is the angular momentum of the system initial? It will be angular momentum of the disk. So it will be I disk omega 0. But now I have to add angular momentum of child C, okay, plus angular momentum of child B, plus angular momentum of child M, just before they jump on the merry-go-round. And this will be equal to angular momentum final multiplied by omega final. By the way, angular momentum final, at the end, all of them will be at the edges. So angular momentum final will be angular momentum of the disk plus mass of child C plus mass of child B plus mass of child M multiplied by R squared. Okay? Because all of them will end up at the edges. Now, what is the angular momentum of C, child C? You see here, the rotation is clockwise, is positive, but the child C has a negative angular momentum. Do you agree with me? Because child C here is rotating, this way, and this is clockwise. So I will have I disk omega 0, and it's a plus. But now angular momentum of child C is negative. It will be minus. Now how to get it? You know that L is just R M V sine phi. So for the child C, R is equal to the radius. Okay, M is mass of C. V will be VC. Sine phi is equal to 90 degrees because he is jumping tangentially. Okay, but don't forget about this minus. Now, what is the angular momentum for B? Now, B, his angular momentum is positive because B, his angular momentum is positive because he looks like he's rotating in the same direction as a merry-go-round. So it will be R, MB, VB, sine 90 degrees, which is equal to 1. What about M? Muhammad, he also has a negative angular momentum. So he will have minus R, M Muhammad, V Muhammad, now sine of the angle theta, because he has a certain angle here. Okay, he is not tangential. And this will be equal to I disk plus M C M B M M R square multiplied by omega final. So the only unknown is omega final. Now my equation is this. I know everything. The only unknown is omega final. I know I disk, I know omega initial is 1.7. I know the radius, I know mass of child C, I know the speed of child C, and I know, of course, this is 1. Here I know everything. This is 1. Here I know everything. This is sine 20. Here I know everything. The only unknown is this gentleman, and I get it easily. Okay. So let me stop here. Please solve the rest of the problem. This is an excellent problem, an A+ problem. Okay. Like exactly. This also is an excellent problem, A+ problem. I don't have time to solve it, unfortunately. Come back to this problem. This, I discussed it in the slides. This is an A+ problem as well. Okay, this is a good problem. Have a look at it. It's good. Solve this problem. It's an excellent problem as well. The solution is given anyway. So just for you to understand this, we discuss it. Which one will arrive first? Okay. This we already solved it. You solve this. This is very good. Okay. Because I want to talk about the origin and then I give you another point. So the torque is R cross F. Now, if I look at the talk about the origin, the R is the position of my particle with respect to the origin. Okay? But if I'm looking at another point, the talk about A is RA cross F. Okay. So you have to find what is the position of the particle with respect to point A, and point A is this. So have a look at it and you solve it. You solve this, it's beautiful. You solve this, you solve everything basically. Okay. This is also a very good problem. Have a look at it. Okay. This is an excellent problem, conservation of angular momentum as well. But here, I did not give you omega. I am giving you the times. Okay. If I'm rotating up. And constant angular speed, omega is 2 pi divided by t. So t is 2 pi divided by omega. So this is what I'm using here. Have a look at it. It's a good problem. This is also a good problem. This is an excellent problem. We already solved it. You can look at this. You can look at this. Everything. Okay. Thank you very much. And I wish you the best, inshallah. Assalamu alaikum.